What is going on, guys? Hope you're doing awesome. In this video, I want to share my solution and show you how to get a really good score on this Kaggle competition from a couple of years back. So the Kaggle competition is dogs versus cats, so it's image classification. And I know some of you are like, wow, why are you doing this one? It's incredibly simple. All right, so let's see what is important. Let's see. So the data, first of all, is 25,000 images of dogs and cats. And we'll take a little bit more in-depth look of the image resolution and so on. But if we look at a sample submission, we can see that we have the image ID and then we have the label. So the labels are actually probabilities. So we're not predicting 0 or 1 sort of binary in that way. We're sort of submitting what the probability is. So in this case, 1 would be dog and 0 would be cat. And if we look at the leaderboard here, we can see that the top has 0.03302. So this score is not accuracy, it is log loss. And so if we, basically what log loss does is so if you give an extremely confident prediction for some label that is incorrect, so if it's extremely confident that it's a cat, but it's actually a dog, it gets penalized extremely harsh for that. And it doesn't scale linearly. So if we look at the logarithm, then you can see that as it goes towards 0, for example, then it gets sort of penalized extremely much, and it doesn't scale linearly. This is binary cross entropy loss or log loss, and that's what they use. So it's very important to know which metric you're optimizing for, right? If we're using for log loss, then we want to make sure that the model is not extremely confident on either side, because if it's wrong, then it will get penalized a lot for that. All right, so if you go to data here and you just press download all and then extract those zip files, then I will show you, we get to this right here. And essentially you get a train and a test folder. I've created a val here as well, but it's empty. So if we have this train here and we sort of sort by size, then if we look at one of them, and this is the largest image size, and let's just take a look at exactly how large this is. So 1000 by 768. And if we go somewhere in the middle, then it's 375 by 500. And then at the bottom, so the smallest image is just 60 by 40. So as you can see, there's sort of a wide range of the image resolutions. And yeah, I guess this is important to check also on the test set. So it seems to be similar on the test set as well. So yeah, basically the distributions are the same. And then, you can see here that in the name of the file, you have cat or dog. So the label is sort of matched in the actual file name. So we'll use that for our data loading. Before I show you how I solved it, it could be a good idea to sort of reflect how you would do it if you were to try to get well in this competition. So what are the sort of the ideas that you have, and what main strategy would you go with, and what things would you try? Yeah, it would be interesting to know before you watch this video what your ideas would be. So if you could leave a comment, that would be very interesting. All right, so let's take a look at exactly what I did. For the dataset, we're going to need some basic imports with NumPy, Pill, Torch, etc. And when creating the dataset class, we're going to send in the root directory where the images are. And then we're going to read the image with Pill and then run it through a transformation for resizing the image to make it a square image, and then also convert it to a tensor. We're also checking what the label is by checking if dog or cat is in the file name. Here I'm just creating a config file, and I like to place hyperparameters, etc. in a particular file. So we're setting things like the device, num workers, batch size, learning rate, etc. And also the transformations that we're going to perform. which is just to resize it to 448 by 448. And yeah, there's no magic here. It just is something just to play around with, and you can see if going smaller or larger is better for performance. For the main script, we're doing some basic imports, and then my idea here first is to use EfficientNet B7 model to extract features from the loaded images and then save those features to NumPy arrays. So that's what you see that I'm coding here. And then I want to train a small model on those extracted features. This way, training should be really, really fast, but at the same time, it should still give really good performance. So all we have to do is get the model pre-trained, and then we want to use our created data set and also create our data loaders, and then use that function that saves the feature vectors, and that's it. All right, so after running for a couple of minutes, we now have basically the extracted features from EfficientNet B7 on this data set. So we have XTrain and YTrain that we're going to use to train the smaller model, and then we have XTest as well. All right, so what I've done here is that I've created a Jupyter notebook where I'm doing logistic regression on these features. So we're having some imports here, and then what we're doing is we're loading those, right, XTrain and Y, and then we are doing a split so that we get a validation data. We're then going to, set this very small so that we train on the entire data set. But basically, we're going to train this logistic regression. Then we're going to predict the probabilities on the validation set, see what the accuracy and the log loss is, and then do the same thing and get the predictions for the test set. And we're going to get that to a CSV, and we're going to name that my submission. So hopefully, this should be really fast to run. And that's sort of the idea with having these extracted features. We can just run this small model and train that really, really fast. All right, so one thing I noticed that I didn't mention is that here I'm also doing clipping the predictions. And that is because of the log loss that we talked about, where I don't want it to be extremely confident because it could be an incorrect classification and then it would be penalized extremely much for that. So here I'm just clipping it so that it's lowest 0.005 and then 0.995. And maybe it's also possible to find better values than these and improve the score slightly also. So here we get a log loss of 0.002. Now we set the validation to 0.1. So either way, we can take those now. So that should be here on the submissions. So my submission. All right, so I'm just gonna drag this over, make submission. All right, and we get 0.03489, which is, that is not bad. We are, let's see, 0.03489. So we're on the top 4 we would be then. Of course, this is an old competition, so it's not really fair, but you gotta have some, you gotta compare it to something. So either way, then we are going to, let's see, we can use a little bit smaller perhaps so we can use more of the training data to actually train this logistic regression model. And yeah, that didn't really help much. A little bit perhaps. Now, what I want to do is see if we can fine tune this model just for one epoch on this cat and dog data set, and basically see if the feature vectors we obtain, if they get better by fine tuning it, instead of just taking the pre-trained B7 model. So what I'm doing here is that I'm just adding and creating a function that takes in the model and the loader, etc., and trains the EfficientNet B7 model and runs through the entire data set once. Okay, so now that the EfficientNet model has been fine-tuned for one epoch, let's rerun the logistic regression and get a new submission, and hopefully the accuracy or the performance will improve slightly. All right, so let's make the submission. All right, and after that, we actually get slightly better. So now we have 0.03265. So if we compare to the leaderboard, this would make our solution the top one. And yeah, it's not fair. This is from a couple of years back. But nonetheless, shows that you can get really good performance just using a pretty simple approach, really. And it didn't take too long. Extracted features and train for one epoch took maybe like 30 minutes. And that depends on your GPU, of course. And then just run the logistic regression goes really quickly. All right, so what are some ideas to take this even better? So I haven't tried these, but I think maybe a neural net instead of logistic regression would probably help on those extracted features. And then maybe an ensemble of neural nets on top of the EB7 features. That would probably also help. And then what you could also do is take an ensemble of efficient net sort of B0 to efficient B7 maybe, and take those features and maybe train a neural net on top of those. What else? So another thing you can do is just use sort of multiple predictions with sort of augmentation. So you could rerun the same image with random augmentation and then use those features and basically do those predictions on all of those sort of images with the augmentations, and then maybe take some sort of average or something. One idea I had was also to use the test set so in an unsupervised way, try to make an ensemble of models and then basically train one model. I've read some paper, I don't really remember which paper this was, but you can use the test set and take the ensemble predictions and train your model on those ensemble predictions. And in that way that should improve the performance a little bit. But maybe this is a little bit sketchy, I don't know. I don't like to sort of use the test set for training, but if it's unsupervised, then maybe. And then just hyperparameters. That's what I would think. If you manage to do these, then I think you can definitely improve the score. How much? I don't know. If you do decide to do an ensemble and stuff, it will be really interesting. So let me know what you get. Anyways, I hope this was useful to get an idea, and let me know how you think the format should be on these Kaggle solution videos. Still kind of figuring that out, but hopefully the main ideas of the solution is conveyed through this video and that it was useful. All right, thanks so much for watching, and I hope to see you in the next video.